Here we're going to talk about exothermic and endothermic reactions. So if we just look at the prefixes to the word, exo means outside and endo inside, and thermic means heat. So exothermic means that you have got heat or energy released to surroundings. So if you have an exothermic reaction, heat energy is released to the surroundings. And if you have an endothermic reaction, it means heat energy is taken in from surroundings. So hopefully the little pictures there will help get that idea into your head. What would you see in the cases? Well, if you had an exothermic reaction, you would see the thermometer increase, so you'd see it get really hot. Endothermic, you'd see the thermometer would be quite low because it's quite cold. So an exothermic reaction would feel hot, an endothermic reaction would feel cold. Now we're going to apply these ideas to a reaction. So the reaction we're going to look at is the combustion of hydrogen. So hydrogen add oxygen makes H2O, and we need to balance that. So if we put those in there, it's balanced. Okay. Now, whenever we're trying to work out if it's an exothermic and endothermic reaction, we look at two parts. We look at the bonds breaking in the reaction and the bonds forming in the reaction. So I'm going to draw out what we have here. So we have H2, but we've got two molecules of them. We have got oxygen. We've got one molecule of oxygen. Notice I've drawn a single bond between the hydrogens and a double bond between the oxygen. And we're going to make H2O. Doesn't matter really in this if you don't draw the correct orientation of the molecules, so whether you get the H2O in the right places, it doesn't matter as long as you're showing the bonds between them. So if I want this reaction to happen, actually I need to do something first. Well, I can't form any of these until actually I've broken these bonds first. So the very first thing you have to do in this reaction is break all of these bonds, and that will leave you with 4 hydrogens and the 2 oxygens. So first I had to break all those bonds. In order to go from these molecules here to these loose atoms here, I've got to break all the bonds, and this requires energy. So energy is needed to break bonds. So this is why if you had things like hydrogen or other fuels, they don't just spontaneously start reacting. They need some kind of energy to start them going, to initiate the reaction. Maybe they need a spark or a bit of heat to break these bonds initially for them then to be able to react. So to finish this reaction, I have all my loose atoms here and now need to form the bonds to create my 2 water molecules. So in this case, energy is released when bonds are formed. So then overall, to decide if this reaction is exothermic or endothermic, all you're doing is looking at the balance between the energy needed to break bonds and the energy needed to form bonds, or the energy released, when you form bonds. So in exothermic, reminder, this means you release heat. The energy released when bonds form is greater than the energy needed to break bonds. So in any reaction you break bonds and you form bonds, but if it's exothermic overall, then the energy released when they form is bigger than needed to break them. Now if it's endothermic overall, in endothermic, so this is when heat is taken in, or heat energy is taken in, in endothermic, the energy needed to break bonds is greater than the energy released when bonds form. So let's review this whole slide. So exothermic, that means heat energy is released. Endothermic, it means heat's taken in, heat energy is taken in. So whenever you have a reaction, the first thing you need to do is you need to break the bonds, and this requires energy. The second thing you can then do is you can release energy because you form bonds. Now overall, if it's exothermic, forming is greater than breaking, and if it's endothermic, breaking is greater than forming. What we're going to do now is try and represent these exothermic and endothermic reactions with their reaction profiles, and we do this in like a graph. So the bottom axis, this is the reaction, and on the y-axis this is the energy. Okay, so the top is the most energy, here's the lowest amount of energy, and as you can see at the start of the reaction we start with hydrogens and oxygens, and they have a certain amount of bond energy. So let's put that on here. So let's say this is their bond energy. So this is our H2 and O2. That's their bond energies. Now, to start this reaction, the first thing I need to do is break the bonds in them. And that requires energy. So first thing we have to do is we have to put in energy to break the bonds. So therefore, my energy profile diagram is going to go up like this. Okay? So that rise is me putting in energy to break the bonds. Finally, now this point here is equal to this point here, where I've got all my individual atoms, my loose atoms. Now what they're going to do is form. Okay? So when they form, they release energy. So that means the energy inside the compound is lower. So they've released all that energy. So let's show how that looks. I would release all this energy, and I would be left with my products. Now my products, H2O. So let's try and analyse what this means. So I need to put in this amount of energy to break those bonds in the first place. This here is the energy given out when I make my bonds from the product, from the top right to the bottom. The difference between these two is this here. And this is the overall energy released. You can see you've released more energy than you had to take in. So let's just add these on. This is energy released, and this is energy needed to break bonds. This is energy released when you form bonds. So overall, we said this reaction will be exothermic, and this is the reaction profile, or the energy profile for an exothermic reaction, because when it's exothermic, the energy released is greater than the energy taken in. So you can clearly see this because the energy released here is clearly greater than the energy taken in, which is why overall you've got more energy released. So the amount, this is exothermic, is this amount here. Okay. Finally, we're going to do the reaction profile for an endothermic reaction. So again, we've got our reaction at the bottom. Let's say this is endothermic. So the idea behind endothermic was that the energy in to break bonds is greater than the energy released. So once again, I'll start with the reactants. I've got this amount of energy. Again, I need to put energy in to break the bonds. Let's take it to there. However, this time, when I form bonds, I'm not releasing as much energy. Okay, so I might only release energy to there and be left with my products. So these are my reactants. These are my products. Here is the amount of energy I need to take in, and here is the amount of energy released. So overall, I have this, and that's overall the energy is taken in. So more energy is taken in than is released, so this is an endothermic reaction, and overall the energy change is shown here in green. The final thing I'm going to share with you is this key term called activation energy. And by definition, this is the energy needed, let's say the minimum energy needed for a reaction to occur. So if you just put two things together and they might collide in the right way, in the right orientation, but if they don't have enough energy to start reacting, they're not going to react. And so that activation energy is this here, the energy that takes you from the reactants up to this point, because that's the energy taken in to break all the bonds in the first place. If you don't have that energy, okay, you're not going to get a reaction happening. So this here is also called the activation energy. Thank you.